Okay, hello everybody, and Merry Christmas for, let's say, Western Christians. It's rather complicated to explain what is it, but everybody who has a holiday today, my congratulations because of it. And in Russia we have no holiday, so this is a usual working day. So we continue our lectures, and today is section 25, let's say point 1, lecture 25th, and this is Taylor's theorem. And I'll start with definition of Taylor polynomial. If f has nth derivative at x naught, then Taylor's polynomial of f at x naught is Pn of fx, or shorter, just Pn of x, equals to the sum k from 0 up to n, k's derivative at x naught over k factorial times x minus x naught power k. That is Taylor's polynomial. So, how it is constructed? Once you have nth derivative at x naught, then of course you have all derivatives of orders up to n minus 1 at a neighborhood of x naught, otherwise you cannot define nth derivative. So all derivatives are well defined at the point x naught, and we construct such a polynomial. Now the first theorem is one. That is just Taylor's theorem. Or sometimes we will add words with Lagrange form of remainder. So if f has the derivative of nth order everywhere in the closed segment, f n plus 1 is defined on the interval AB, then for every x naught in AB, and for any x in AB x not in fact doesn't matter, x not equals to x not, let it be. there exists C in between x naught and x such that f of x equals to Pn of x plus f and derivative of order n plus 1 at c over n plus 1 factorial times x minus x naught power n plus 1. So, or maybe let me add where Pn of x equals to Pn of fx is the Taylor polynomial of f at x naught. Okay. Let's analyze a little bit the assertion of Taylor's theorem. So look, you see that this sum consists of several terms, and in fact the first terms are constructed in a very similar manner to the last one. So what is different? You see, every term in Taylor's polynomial contains the derivative at x naught, and the last term contains the derivative at a point C. In fact, we cannot control the position of that point, so it is somewhere in between. That's all what we know. And you see that this is some kind of approximation of arbitrary function with sufficiently many derivatives. So if a function has n plus 1 derivatives in an interval, then you can write such a formula. Okay, proof. Let us denote by lambda a real number which is well defined by the equality. So f of x equals to Pn of x plus lambda over n plus 1 factorial times x minus x naught power n plus 1. So that's equivalent to say that lambda equals to n plus 1 factorial times f of x minus Pn of x over x minus x naught power n plus 1. The denominator is not 0 because of our supposition, x naught equals to x naught. So that is the definition of this number lambda. So we fix both x naught and x. Both are fixed, and then this is a well-defined real number. Okay, now we consider a function. So put g of t equals to so we just write down I will not use p and fx, because what we want, we write something similar to what is written, but so f of x minus what I want to write down is precisely this expression, but everywhere instead of x naught I want to put t, so it will be minus sum k from 0 to n derivative of kth order at t over k factorial times x minus t power k plus lambda over n plus 1 factorial times x minus t power n plus 1. Yeah. By our suppositions, this function is well defined for t in the segment AB, everywhere in this segment. Why? Because we have derivatives up to order n at t, and according to our supposition, all those derivatives exist everywhere in the segment AB. Okay. Now, what is about properties of that function g as a function of t? So, once again, we fix both x naught and x, and in fact we consider the segment with ends x naught and x. So it means either x naught x or x naught. Depends on where x naught is located. So what can we say about this function as a function of t? X and x naught are fixed. In fact, x naught is not here, but x you can see. So since maybe to make it easier, let me, if f has continuous fn everywhere in AB, because I don't want to exclude cases x naught or x equals to a or b, right? So if we add this additional supposition, then what can we say? All those derivatives of arbitrary order up to n are continuous everywhere on the segment AB, in particular everywhere on that segment which is interested for us. Also, other functions of t are polynomials, hence they are continuous as well, and it means g is continuous here. So g is continuous here. g is continuous here as a function of t. Next, what is about derivative? If we'll try to differentiate, then you see polynomial can be differentiated without any problem, and the only possible difficulty appears when we try to differentiate the derivative. And of course, in fact, the problem is for k equals to n. So nth derivative, it should be differentiable on an interval x naught x or x naught correspondingly. So what is about that interval? That interval definitely is a part of the interval AB, because it doesn't include n's. So even in the case when x naught or x coincides with one of n's of the segment AB, there is not a problem for the derivative of the order n plus 1. So the derivative of n plus 1 is defined everywhere in that interval. Hence, g is differentiable everywhere on this interval. So g is continuous on the segment and differentiable on the interval. Now let us consider its values at the ends. So g of x naught, let's start with it. If we substitute instead of t x naught, then this will be f of x minus, then what is in brackets? The first sum, if we substitute x naught instead of t, the first sum will be nothing else but Taylor's polynomial. So the first term is the Taylor polynomial, and okay, then we write x minus x naught power n plus 1. But now we remember the definition of the number lambda. So lambda was defined in such a manner that f of x equals to this sum. So because of the definition of lambda, the difference is 0. Now what is about g of x? So it means we should substitute instead of tx. So the first term is not changed. And what is about terms in brackets? Here for k equals to 0, let me write what we have. If 0's derivative is just the function itself, so I should substitute instead of tx over 0 factorial, which is 1, times 0th power is 1, times 1, plus, what's about other terms? Other terms, k from 1 up to n. Okay, let me write firstly k's derivative, let it be k factorial, and then we substitute x minus x power k. And same story with the last term. So, what is it? These are zeros. Those brackets are zeros. So, all terms in large brackets are zeros except for the first. The first is f of x, so we cancel with this f of x, and that is 0 again. It means the function g satisfies Rolle theorem. So, we can deduce by Rolle theorem there exists C in between x naught and x such that g prime at C equals to 0. Because of, once again, Rolle theorem. The values at the ends of our segment equal to 0, and all other conditions of Rolle theorem are satisfied. Okay, so now we should compute the derivative. Okay, let's compute it. Remember that we should differentiate with respect to t, and we consider x as a fixed number. It means f of x here is constant. Derivative of constant is 0. So I'll put 0 minus. Now, once again, it's better to write down separately the very first term for k equals to 0 and all other terms. They will be differentiated in slightly differently. Okay, so for k equals to 0, what we have here, k equals to 0, we have f of t and nothing else. So after substitution, instead of tx, we had here f of x, so f of t, just f of t. So the derivative is precisely f prime at c. Instead of t, we substitute c. Then we should differentiate all other terms of the sum for k from 1 up to n. We should differentiate as a product. Okay, 1 over k factorial, of course, is a constant. And then as a product. So differentiating k's derivative gives the derivative of the order k plus 1. Again at c, of course, and we should multiply by x minus c power k as it was. So that is the derivative of the first term times second, plus the first term, k's derivative at c instead of t, and then we should differentiate x minus t power k. It gives k times x minus t power k minus 1 times derivative of x minus t. Let me recall that, okay, instead of t I should substitute c. Derivative of x minus t with respect to t is minus 1. So times minus 1. That is how we differentiate all terms of the first sum, of the first sum. Now we can differentiate the last term, so plus lambda over n plus 1 factorial is a constant, and we differentiate x minus t power n plus 1 like we did with this term, so it gives n plus 1 times x minus t power n times minus 1. That's it. Once again, instead of t, I should substitute c, right? I forget. So we differentiate, and then we substituted everywhere. Instead of t, we substituted c. Okay. Now, let us write it down term by term. So, minus f prime of c, the first term. Then, minus, let me write down k equals to 1. So, k equals to 1, what it gives? F second derivative at c times x minus c power 1 minus and minus 1 minus is here, so plus. Then I'll write this term with k equals to 1. It gives f prime at c, k equals to 1, so nothing else. Next term, k equals to 2. Once again, minus, k equals to 2. 1 over 2 factorial times f second, k equals to 2, third derivative at c times x minus c power 2, right? Then once again, minus gives plus. Don't forget this term, 1 over 2 factorial. times what? Now I should multiply by this, k equals to 2. F second derivative at c times 2 times x minus c power 1. Minus, so on. So, the very last term with k equals to n, let me write it down, minus 1 over n factorial times f derivative of order n plus 1 at c, right, yeah, times x minus c power n, k equals to n. Then next term, once again, minus gives plus, so k equals to n, 1 over n factorial, it's still here, f nth derivative at c, k equals to n, times x minus c power n minus 1. That is, nth term is written now. So all terms of that sum are written here explicitly, and now the very last term, that is just a minute. It seems, yeah, it's okay, yeah. So minus is here, right? Yeah, minus is here, so minus gives plus lambda over, okay, we may cancel n plus 1, n factorial, x minus c power n. That's it. So that is the derivative of the function g at a point c. Now we observe that what we have here is just telescoping sum. So look, f prime, right? Then here we have minus f second derivative at cx minus c plus 1 over 2 factorial times 2 we cancel, so again cancel this sum. And of course this sum will be cancelled with the next one, so this term with nth derivative will be cancelled with former. The only term which has no pair is that term with highest derivative of n of order n plus 1, right? Okay. And so, and once again, let me recall that g prime at c, according to Rolle theorem, is equal to 0. So you see everything is cancelled. What is not cancelled is that one. And that is precisely, look, now if you write this equality, x minus c power n over n factorial is a non-zero common term. Why it is not 0? Because according to Rolle theorem, c is in between, strictly between. So in the interval, in fact, right? By Rolle theorem, we guarantee c is somewhere in the interval. It means x minus c is not 0. And if we cancel, then we obtain that lambda equals to f n plus 1 of c. And that is precisely, look, what we wanted to prove. What we wanted to prove. The proof is complete. Okay. Example. Maybe I should erase everything except Taylor's polynomial. No question. Everything is clear. Great. Great. Okay. So, example. Estimate the error in approximating the function f of x equals to sine x with It's third Taylor I forget to insert here nth Taylor. Third Taylor polynomial at x naught equals to 0 on minus 1, 1. Okay. So first of all, let's construct Taylor's polynomial. So we write the derivatives, cosine, second derivative minus sine, third derivative minus cosine, and fourth derivative is again sine. Or maybe we can do without break, right? Because of late start. Okay, so we should construct third Taylor polynomial. It means we should compute derivatives at x naught, and x naught is just 0. So that is 1. Second derivative at 0 is 0. Third derivative is minus 1. It means third Taylor polynomial P3 of fx, P3 of x, is just the following. So, okay, maybe I'll write firstly in general form, k from 0 up to 3, k derivative at 0 over k factorial times x to the power k. So, yeah, the function itself I should write also, right? F at 0 is 0. Sine 0 is 0. So, k equals to 0, k equals to 2 terms with k equals to 0, k equals to 2 disappear. And what remains? K equals to 1. First derivative is 1, so we have x. And k equals to 3. Third derivative minus 1, minus 1 over 3 factorial. 3 factorial is 6, so x cubed over 6. That is third Taylor polynomial at x naught for the function sine x. Now, we can apply Taylor theorem. So, Taylor theorem says that the difference sine x minus p, or maybe I'll write p equals to p3 of x plus, so Taylor theorem says the function equals to Taylor polynomial plus next n plus 1 is 4, fourth derivative at c, so sine c over 4 factorial times x power 4. That is the conclusion from Taylor theorem. Now we can estimate the error. So the error is the difference between sine x and third Taylor polynomial. that is equal to sine c over, okay, 4 factorial, that is 24 x power 4. And we should estimate it on the segment minus 1, 1, so modulo x less or equal to 1, and sine c is always less or equal to 1 as well, so less or equal 1 over 24. So that is the desired estimate. Yeah, in fact, it is written what it is approximately 0.042. Okay. Now I'll skip to subsection for a while. Yeah. And let us introduce usually they're called, in Russia at least, Landau symbols. Same Landau as was mentioned at the beginning of our lectures, who wrote a nice book about theory of numbers, axiomatic theorem, starting from naturals. And so what are symbols? Okay. Definition. In fact, we can define both for infinitely large and infinitely small functions. But in principle, we can do without those suppositions. So just okay, let g of x be not equal to 0 in a punctured or deleted neighborhood b not of x naught, what is x naught minus delta x naught plus delta without x naught. If limit as x tends to x naught f of x over g of x equals to 1, then f of x and g of x are equivalent as x tends to x naught. Okay, usually we should suppose here, so usually for limit as tends to x naught f of x and g of x is equal to either 0 or plus or minus infinity. So usually this definition and all others, there is a question. Great. What is the error? the error in approximating. The error in approximating is precisely this modulo. So Taylor polynomial is something what approximates our function sine x. So Taylor polynomial approximates sine x. So the error is what is the difference between the true value of sine x and its approximation in modulus. That is what is the error. Okay? So, okay, let's return to our definition. So once again, so formally, the definition of equivalence between functions f of x and g of x, you can write, so once you have such equality, then you can say the functions are equivalent. But usually it is applied for the cases when both are infinitely small or infinitely large. And same is true, by the way, for all other definitions, all other parts of the definition. In fact, that is a long definition. So let's continue the definition. So we say if f of x over g of x less or equal than m in a deleted neighborhood of x naught for some real, right? Then f of x is big O of g of x. Big O. Big O. And if limit as x tends to x naught f of x over g of x equals to 0, then f of x is O of g of x. Little o. Little o. And usually we should add here x tends to x naught, and yeah, I forget to write notation for equivalence. For equivalence, f of x is equivalent to g of x as x tends to x naught. That is the notation. Okay, these are symbols. Maybe small example. X squared of x cosine x sine squared x of x tan cube x sine 1 over x of x squared, modify a little bit as x tends to 0. So let's check those equalities. So the first one, limit as x tends to 0, x squared over x is equal to limit of x is 0. Then it follows the first equality. All others can be checked similarly. So limit as x tends to 0, cosine x over sine squared x over x, Sine x over x by the first remarkable limit is 1, so what remains cosine x times sine x, and that is 0. So it gives the second. And for the last limit, as x tends to 0, tan cube x sine 1 over x squared, that is limit x tends to 0 tan x over x squared times limit tan x times sine 1 over x. So sine 1 over x is a bounded function. Tan x infinitely small tends to 0, so the product tends to 0. And there is sine over cosine. Cosine tends to 0, sine x over x. The first remarkable limit equals to 1, so we have again 0. 1 times 0 gives 0. And that is the last. Okay. And yeah, in fact, quite usual when we use all those definitions for x naught equals to infinity, plus or minus, and that is also used quite often. Okay, so now next Taylor theorem. And for that next Taylor's theorem, we'll need a lemma. And to formulate that lemma, it's better to use one more notation. So definition or notation, remainder of Taylor's formula is defined as Rn of fx equals to f of x minus Pn of fx. So we consider the difference between the function and nth Taylor polynomial. So remainder, or in other words, it's the same as error of approximating by the function by the Taylor polynomial. Okay, so now lemma. If f has, okay, derivative, let's say, okay, nth derivative at x naught and f prime in neighborhood of x naught. In fact, I don't need to suppose it. It follows. It follows. Then, okay, maybe I should n greater or equal to. Then derivative of the remainder equals to n minus 1 f prime x. In a neighborhood of x naught. Proof. Proof. So, we want to differentiate the remainder. It means the difference between the function and its Taylor nth Taylor polynomial. So, if the function has at least second derivative, then the first derivative should be defined in a neighborhood of x naught. Hence, we can differentiate f. It gives f prime of x minus. Now here x naught is fixed, so that is a constant, minus some. Okay, firstly, let me observe that for k equals to 0, what happens for k equals to 0? K equals to 0, this term is 1, so we have just a constant. Derivative of constant is 0. That is why only sum for k from 1 up to n remains. So the constant is preserved in differentiating. And then what we have? We should multiply by k, and then the derivative x minus x naught power k minus 1, and by chain rule derivative of x minus x naught is 1, so no extra terms appear. Okay, let us replace here k over k factorial is k minus 1 factorial, so let's replace k minus 1 by, let's say, m. Then we can rewrite it as f prime of x minus some m now starts from 0 up to n minus 1. And k's derivative can be written as now derivative for the m plus 1. And that is derivative of order m of the first derivative, x naught, over, here we have k minus 1 factorial, so m factorial times x minus x naught power m. And you see, this is nothing else but the n minus first Taylor's polynomial of the derivative. So we have the remainder for derivative as we wanted. That's it. Lemma is proved. Lemma is proved. Okay, next theorem is very popular in Russia, but is not used in most part of Western textbooks, and it means that most part of exam questions which are used here in a written exam cannot be solved by most part of students from Western universities by definition, because of they don't know this way. They don't study it. So that is next theorem, theorem 2, which is called Taylor's formula. With remainder in Peano's form. Okay, if f has derivative at x naught, then f of x can be represented as its nth Taylor polynomial plus o little o of x minus x naught power n as x tends to x naught. Okay. Proof. We'll proceed by induction. Let's start with n equals to 1. F prime at x naught exists. Hence, we can write f of x equals to, by the definition, f of x naught plus f prime at x naught times x minus x naught plus alpha of x times x minus x naught, where limit of alpha of x as x tends to x naught equals to 0. It follows from the definition of derivative, and we mentioned it. It was a theorem, in fact. That, in fact, we have if and only if here. Okay. Now, let's observe that this is nothing else but first Taylor polynomial at x naught and the last term alpha of x times x minus x naught is little o of x minus x naught power 1 as x tends to x naught, just because of this. So if we divide by x minus x naught, then it tends to 0 because of the supposition about alpha of x. So n equals to 1 is proved. Now, suppose we have proved the assertion for n equals to m minus 1, the induction hypothesis. So what is the induction hypothesis here? We suppose that once we have a function which has m minus 1 derivatives at x naught, then we can represent f of x as a polynomial of order m minus 1 plus o small of x minus x naught power m minus 1. Now consider n equals to m. So we should prove our assertion. So it means that what we want is to prove that this equality holds. X tends to x naught. That is what we want to check, right? Yeah. Okay, so now I should use the Lagrange mean value theorem. So we'll use it for the left hand side. So look, it means we consider the left hand side is just the remainder. So we consider the function Rn fx. The polynomial is differentiable everywhere, and the function has a derivative of, okay, n equals to m should be at least greater than 1, so it means at least the first derivative should be defined in a neighborhood. So Rn fx is differentiable in a neighborhood of x naught. Okay. Then we can apply Lagrange mean value theorem. Lagrange mean value theorem for the segment with ends x naught x, or x naught depending on where is x. So there exists C in between, so C somewhere here. C belongs to one of those intervals, such that Rn of f x minus Rn f x naught equals to Rn f x, I write like that, prime for x equals to c times x minus x. That's it. Okay. Now, we can use the lemma. So we can rewrite, and also what is Rn fx naught? So Taylor polynomial, look, Taylor polynomial at x naught is nothing else but f of x naught. So that is 0 in fact. The remainder at x naught is 0. So using the lemma, we can rewrite Rn fx as Rn minus 1 f prime c times x minus x naught. Now consider the derivative f prime. By the supposition about f prime has the derivative of order n minus 1 at x naught. And you see, if n equals to m, then here we have just m minus 1. So, or maybe I'll put here just m minus 1, right? It means that we can apply the induction hypothesis, for the function f prime. So, induction hypothesis implies that the remainder of f prime c equals to O small of c minus x naught power m minus 1 as c tends to x naught. Let's substitute it to form a formula. So we can write n equals to m, let it be m now, it's more convenient. So that is x minus x naught times little o of c minus x naught m minus 1 as c tends to x naught, right? Now I claim that this is nothing else but little o of x minus x naught power m as x tends to x naught. That is what we have to prove, in fact. Why? By the definition. What means this equality with O small? By the definition, to prove this equality means that I have to check if limit as x tends to x naught, x minus x naught times little o of c minus x naught power m minus 1 over x minus x naught power m if it is 0 or not. But I can write it like that. Limit as x tends to x naught. Okay, I may cancel x minus x naught. And we have also little o of c minus x naught power m minus 1 over c minus x naught power m minus 1 times the ratio of c minus x naught power m minus 1 over x minus x naught power m minus 1. Now, we have a product of two ratios. The second ratio, modulus c minus x naught over x minus x naught, in fact, you see, c is somewhere between x and x naught. Hence, modulo of c minus x naught is strictly less than modulo of x minus x naught. Hence, this is less than 1. So we can also take arbitrary power, let's say m minus 1. So the second ratio is bounded. And the first ratio, by the definition of little o, tends to 0 as c tends to x naught. But if x tends to x naught, then, since c is between x and x naught, so x tends to x naught implies c tends to x naught as well. Hence, what we obtain? We obtain a product of a quantity which tends to 0 times a bounded quantity. So the result is 0 as we wanted, and it means we have proved. So the theorem is proved by induction. Okay. Yeah, and now I have only 3 minutes remain. So maybe okay. Next lecture we have tomorrow to fulfill the required 30 lectures. So tomorrow we'll continue with Maclaurin formulas for elementary functions, and I should give a definition, and maybe I'll finish with this definition. So, definition. Taylor's formula for x not equals to 0 is called Maclaurin formula. So, it means, like in example which we had today, x not equals to 0, so it means what we wrote, let me recall, sine x equals to x minus x cubed over 6, right? This was example from today. And now there was an error, right? And now we know that we can write this remainder as little o of what? Of x to the power 4 as x tends to 0. Why? Because in fact, this is not only P3 but P4 of sine x. Fourth Taylor polynomial. Why? Because recall that if we have f of x equals to sine x, then fourth derivative is also sine x. So fourth derivative at 0 is 0, and it means that what is written here is precisely fourth Taylor polynomial, and that is Maclaurin expansion or Maclaurin formula with remainder in Peano's form for sine x up to order 4. Okay, so, and please don't use your lecture notes in exam. I mean, Maclaurin expansions. Why? Because Maclaurin series will be considered essentially later, and if we'll use Maclaurin series in exam, I may ask you, what is it? And please prove. And you will be not able to do it. So be careful. Don't try to write down Maclaurin series in exam. We'll prove them later in next semester. Okay, that's all for today. Thank you.